Hello class, this video is going to cover analysis of variance. First things first, the first student who posts on the discussion board and says yay stats is going to receive a bonus, 5 points on the upcoming exam. So again, first person to say yay stats on the ANOVA or analysis of variance discussion board, 5 points bonus. Just looking to see how many people are actually watching these videos, which people are watching them first. So for analysis of variance, typically we are comparing 3 or more groups, but technically analysis of variance can be used to compare 2 or more groups or 2 or more conditions. And when we talk about it as groups or samples, then typically we're doing what's called a between subjects ANOVA. And if we're comparing conditions and we have the same people across conditions, then it would be a within subjects or repeated measures ANOVA. So we have the two different types depending on what we're using. This first video is going to focus on between subjects. It's also going to focus on what's called a one-way ANOVA. So with the one-way ANOVA, we have one factor like gender or SES, like socioeconomic status or ethnicity, and we're comparing groups across that factor. With a two-way ANOVA, we are comparing two different factors to look and see if they have a benefit. So if we think that, for instance, ethnicity and gender would impact SAT scores, we could use a two-way ANOVA. This video is going to focus on a one-way between subjects ANOVA. So when we talk about a one-way between subjects ANOVA, an example would be if we wanted to look at salary across education type. So we have 4 education levels, and here we see less than high school, bachelor's, graduate. We could of course include more. We could talk about an associate's, what's the benefit of that. You do see a benefit from having an associate's degree, but for ease we're just going to use these 4. And you could then compare across these 4, although you would need the original data or you would need some variability estimate. So just having these averages, which I really did pull these from the Bureau of Labor Statistics. So these are correct for, I think, 2019. Those are the differences. So having a graduate degree, having a bachelor's degree will in fact benefit you, and you'll make about $23,000 more by having that degree. So congratulations. Hopefully that'll pay off your student loans pretty quickly. Now we could split this up and we could look at education by gender, and that would be a two-way between subjects ANOVA. This is one way to visualize that, where we have education, still those 4 categories, and then we have education between men and women to look and see, is there differential impacts of getting higher education by gender. And unfortunately, like I said, these data are real data, and as you can see, there is still quite a bit of a gender disparity in regards to income. So ladies, feel free once this quarantine thing is over to pick up a torch and start talking to people. I think realistically, keep in mind that there is this disparity, and sometimes you'll see it whenever you are applying for jobs, whenever they make you an initial job offer. And so, explore company salaries, see if there's a gender inequalities, try to negotiate. And so we do see that part of this is because men tend to negotiate their salary more than women. Still doesn't necessarily excuse it, but at the same time, you can potentially help to reduce this difference by negotiating a little bit more. And so that would be one fairly easy personal way that you could try to change this, alter this. Some abbreviations that you need to know. You've seen N, capital N and lowercase n before. What is new is K. So K is our number of groups or our factor levels. So if we're comparing men and women, K is 2. If we are comparing education, for instance, less than high school, bachelor's, graduate, we have 4 groups, so K would be 4. And then little n here is used for our number of participants in each group. And we talked about before how little n and big N can be used in a couple of different ways, but they're always relatively consistent to each other, or at least consistent relative to each other, because little n is always going to be the smaller of the 2, and big N is going to be the more inclusive of the 2. So before, we typically use little n to indicate our sample, big N to indicate our population, which is larger, bigger, more inclusive than our sample. Here, we're going to use little n for each group, and we're going to use big N for the total participants across all groups. So that's going to be the more inclusive of the two. Some of the formulas that you're going to need to know. The main statistic for is there a difference between these groups is going to be the F statistic. So F obtained compared to F critical. And just like before, you're going to use a table. In the second video where I walk through an Excel example, I'll show you how to compare F obtained to F critical because the table is a little bit different than what we've seen before. For F obtained though, the ratio is still similar to what we've seen before, where it's the between group difference. So before we had X bar minus mu, for instance, if we were doing a one sample t-test. It was the difference though between our sample and the population. So still your numerator is going to be the difference between your two groups, or between your three groups or four groups or how many ever. And the way that we get that difference is the mean squares between, and we'll talk about how to calculate that in a little bit. We're then going to divide that difference by the within group variability. Before, we used the standard error of the mean that was based on standard deviation. And so for the t-test, we use variability, standard deviation, within the group. And for the z-test, we use standard deviation, variability that was from the population. But we still did the difference divided by the error, divided by the variability that wasn't explained. And we're doing that same thing here, where we have the difference between our groups divided by the variability within the groups. And then this distribution, because of the way that it's set up, typically centers around 1. It does look a little bit different depending on the number of degrees of freedom that you have. And we'll talk about degrees of freedom here in a moment. But it typically is going to peak around 1, with values that are higher being less and less likely. So as the difference, the ratio of the difference between groups divided by within groups gets larger, then it is less and less likely. For the degrees of freedom, the degrees of freedom between, which in the table here is marked as degrees of freedom 1, degrees of freedom between, or sometimes you'll also see this as degrees of freedom effect, is k minus 1. So that's the number of groups minus 1. Degrees of freedom within, sometimes you'll see it as degrees of freedom error, is n minus k. And then the total degrees of freedom is the total number of people minus 1, so n minus 1. Now these formulas are consistent with what we've seen before. So whenever we were doing the independent samples t-test, it was n1 minus 1 plus n2 minus 1. And I said that basically you could abbreviate that or kind of restructure that as big N minus 2. Well, how many groups did we have in an independent samples? It's always 2. So really this is just an extension of a generalization from N minus 2, where 2 was K, 2 was the number of groups. It's easy in an independent samples because it can only ever deal with 2 groups. In an ANOVA, it can deal with more than 2 groups, and so because of that, we need to use a variable that can be more generalized. So that's where we use K, and K will be our number of groups each time. For mean squares between, this is going to be equal to the sum of squares between divided by the degrees of freedom between. And one of the easiest ways to kind of talk about this is to visualize what is sum of squares between in this analysis. So sum of squares between is going to be the x bar for your group minus the grand mean. And by grand mean, that is the mean for everybody. And then what we're going to do is see how far does the group for each person, how far is that from the grand mean? And we're going to have to do this for each person. So just like before, whenever we would do squared deviations and we had to do it for each individual, we still have to do it, but we're using that group mean instead of the individual score for the sum of squares between. And then we divide that by degrees of freedom between, which would be k minus 1. For the mean squares within, this is going to be similar to what we've done before. We still have to do it for each individual. And again, we'll show you that in Excel in the second video. And what we're going to do is sum the squared deviations of the individual from their group mean. And you will have to adjust it so that you use the appropriate group mean. So the individuals in less than high school are compared to the mean for less than high school. And then the individuals that have a high school education are compared to that mean. And so we're seeing how far does that individual deviate from their mean. We then square it because some are going to be above it, some are going to be below it, just like before. And then we sum all those squared deviations together across the total number of people in our sample. We still need effect sizes because we can, just like with other things, kind of inflate the significance by increasing the sample size. And eta squared is one of the commonly used measures. You can do a Cohen's d, and I think your book may cover that, but eta squared is another effect size measure that you can use for an ANOVA, and it's simply the sum of squares between divided by the sum of squares total. So basically this gives us the proportion of variability that is due to between group differences divided by the total variability, divided by the variability of the individual around the grand mean. So the sum of squares total is going to be equal to the individual score minus the grand mean, and then you're going to square that deviation, you're going to square that difference. These are a lot of formulas. I don't deny it. To help you understand them, you can see that these are now organized. So we have our three types of sum of squares. We have the sources of variability in the far left. So we have the between group, which is how far is an individual's group mean from the grand mean, and then we square it and add them all together for each individual. Our within group is how far is the individual from their group mean. So if somebody has a high school education and their salary is above the average for high school, how far above that average are they? And then we have the total, which is how far is the individual from the grand mean, the mean for all pupils that are included in the analyses. We also have our three sources of degrees of freedom. So the degrees of freedom between is based on the number of groups, minus 1. Degrees of freedom within is the total number of individuals minus the number of groups. And then the degrees of freedom total is going to be the total number of individuals minus 1. We can then use sum of squares and degrees of freedom in each of these categories, each of these sources of variability, to calculate the mean squares for between and the mean squares for within. And so if you take sum of squares, divide it by the appropriate degrees of freedom, either between or within, you then get the mean squares between or the mean squares within. And then finally, we can use mean squares between divided by mean squares within, and that quotient of mean squares between divided by mean squares within is going to give us our F ratio. The overall test, often referred to as an omnibus test, is useful. It tells us, is there a difference in salary between these education groups? So we're going to flip back real quick. So is there a difference between these? Now what that primarily tells me is probably, is there a difference between less than high school and a graduate degree? I wouldn't be surprised if we find that, especially if we have an adequate sample size and we have enough power. But it doesn't necessarily tell me, is less than high school going to be different than high school? What is the benefit? Is there a significant benefit of getting a high school degree? Now looking at these raw numbers, $10,000 seems like a lot. You're almost taking and multiplying your salary by 1.3, right? You're almost getting a third of the money extra every year for the rest of your career by getting that high school or GED diploma. Now, is that significant though? And is getting a graduate degree going to significantly improve your earnings over just having a bachelor's degree? That we don't know from the omnibus test. When we get that F value, it just tells us, is there a difference somewhere within this data? These post-hoc tests help us to know, where is that difference occurring? And so for our example, where we have less than high school, bachelor's, and graduate, we actually could do multiple post-hoc tests where I compare high school to less than high school. I compare less than high school to bachelor's, less than high school to graduate. I can then also compare high school to bachelor's and high school to graduate, and I can compare bachelor's to graduate. And so within those four groups, you can see that there's actually a number of comparisons that can be made. And so this formula says x1 minus x2 or x bar 1 minus x bar 2. We actually can use x bar 1 and x bar 2 to mean multiple different things. That's the reason I put 1 and 2 as opposed to a group, because x bar 1 could be less than high school compared to high school, where x bar 1 is less than high school, x bar 2 is high school. Or it could be less than high school compared to bachelor's, where x bar 1 is less than high school, x bar 2 is bachelor's. And so we can make all pairwise comparisons for that. And this is very similar to the t-test. If you look at the formula for this compared to the formula for the t-test, it's basically the same, where we have the difference between our two groups divided by the standard error of the mean. The difference here is when we make the final decision, the critical value is adjusted for the number of comparisons that we are making. So our cutoff is going to be a little bit more stringent. It's going to be a little bit higher than it would be if we used a t-test by comparison, because we have to pay a price for the number of comparisons that we are making. Basically, our p-value or our alpha level has to be divided by the number of contrasts. And we're not going to go into that much more. We'll stick with just generally how do you use this, how do you do this. But this allows us to make multiple pairwise comparisons and accounts for the number of comparisons that are going to be made.